Our notes today go into a topic called deductive reasoning. So we've looked at inductive reasoning and how we can try to come up with a rule about the world around us based on observations. Deductive reasoning is the more common kind of reasoning that you use in like puzzles and games and things like that. So this is taking rules that we already know about how things work and applying them to come up with conclusions. There's two main ways that we do that. So in our notes today, we're going to look at something called the law of detachment, as shown here, and the law of syllogism. So these two together form the foundation of what we call deductive reasoning and are basically how we logic things. So we build the law of detachment on a conditional. So conditionals, recall, we have something like if P then Q. So that says if P is true, it just says if P occurs, then P also occurs. It kind of links these two together. We can think of that as a Venn diagram with a set and subset. So the second thing here is the big circle, and the first thing is the smaller circle. So this says if P, then definitely Q, meaning P must be within Q, right? So everything in the circle, the smaller circle, is also in the bigger circle. So we have the two parts of this, as we talked about with conditionals, are hypothesis and conclusion. So we can think of the hypothesis is a subset of the conclusion, is one way of framing it. So what the law of detachment states is we know if P then Q, and we know P. And we can conclude, we use this little 3 dot symbol, meaning therefore. So this means therefore, we can conclude Q. So if we know if P then Q, that's a given information, and we're given that P is true, then Q is also true. So this hopefully seems pretty obvious, and in this version of logic, we're not questioning these. So these are given, and we accept them as being true. So we're not questioning whether this conditional is true or whether P is true. If it's given information, they are true, and we're just able to conclude that Q is also true. If we're questioning these, that's a whole separate thing. So questioning the conditional here happened when we did inductive reasoning. So inductive reasoning is where we came up with this conditional in history, and now we believe that it's always true, so it's just part of our given information that we can work off of. Hopefully that makes sense. So within law of detachment, there's kind of two main things to think of. We know if P then Q, and we're given P, then we can conclude Q. That's the basic version. But we also have, when we looked at conditionals, something called the contrapositive of this statement. And we said that those two things are logically equivalent. So this is our, I guess I should put conditional, not statement. So let me put a label here. This is our conditional, the original version. And then our contrapositive is a logically equivalent statement that says if not Q, then not P. So that's kind of the opposite version of that. So we can use this law of detachment in two ways. We can say if P then Q and we know P, we can conclude Q. But we can also take this logical equivalent version and say if P then Q and not Q, we're allowed to conclude not P. And I think the Venn diagram is really helpful for visualizing this. So the first one says if our dot is inside of the small circle, it also has to be inside the big circle. Whereas this version down here says if our dot is outside the big circle, so it's not in Q, then we know for sure it's also not in P. So these two, we can make valid conclusions, but we can't make any conclusion about something in between. So, for example, an invalid conclusion in the way that we misuse the law of detachment is we know if P then Q. If we know Q is true, it is invalid to determine that P is true. So we're going to put a big red X by this one. That is invalid. And again, the Venn diagram makes it really easy to see why, because I have a dot right here that is inside of Q, but is not inside of P. So this does not work out to put it this way. And that's the idea that we had with an converse statement. The converse says if Q then P, and this is not logically equivalent. These are two separate statements that do not necessarily go together. So just the last thing on here, this doesn't mean P is false either, right? So if we know if P then Q, and we know Q is true, P might be true, because my purple dot could be here outside of the P circle, or it could be here inside of it. If I just know that it's inside of the big circle Q, I don't know where it is. So this one, we can't conclude P. We also can't conclude not P. We can't make any kind of conclusion about whether P is accurate or not. So hopefully that makes sense, that we have kind of three cases that we're looking at. Our conditional, I'm going to change the color. Our conditional was this original green dot, where we know that it's inside the small circle, so it has to be within the big circle. The second one, let's make that yellow. The contrapositive version tells us that the dot is outside of the big circle, so we're positive that it's outside of the small circle as well. And then the version that doesn't work with the purple dot is where we know that it's outside or inside of Q. We don't know if it's inside of P or not. Likewise, if we look at the inverse, let's do the inverse in this weird color. So the inverse was not P. Oh, it's broken line. Let's not do that color. Let's do this purple color. We already kind of did that color. Let's just do black. So the inverse said not P, then not Q. So this one, just like the converse, is not logically equivalent to our original statement. So we can find a dot that's outside of P and is inside of Q, or outside of P and outside of Q. So we don't know anything for sure about these two because they're not logically equivalent to the original statement. So that was a lot of stuff here. Hopefully, based on stuff we've already learned, it made sense and you can follow along with it. But the main idea right here is the left side that says if we have our conditional and the hypothesis is true, the conclusion's true. Or if we have our conditional and the conclusion is false, the hypothesis is false. All right, so let's look at some example problems. Hopefully this will make good sense for you. So we're using law of detachment to write a valid conclusion if possible. And the way we do this with sentences is we turn things into symbols. So just like we saw with P and Q, we're going to say if Mark saves $30, then he can buy a new video game. So P represents saves the money, and Q represents buy the game. So we say if, and this is not the conclusion, I'm just using the space to write, if he saves the money, then he can buy a new video game. So Mark saves $30. That means our second statement, P, is true. And we know that since we have this conditional and the hypothesis is true, then we can conclude, therefore, Q is true. That means our conclusion is true. He can buy a new video game. Second one, if a quadrilateral is a rhombus, so P is if it's a quadrilateral, and Q is it is a rhombus, then if a nope, I was wrong. That tricked me. So I don't even know where an eraser is. Let me just undo. Okay. If a quadrilateral is a rhombus, then, that's the important part, so a quadrilateral is a rhombus, then it is also a parallelogram, is Q. So P says it is a rhombus, and Q says it is a parallelogram. So we know quadrilateral ABCD is a rhombus. So we had if P then Q. And then this part, quadrilateral ABCD is a rhombus, matches P, so we know P is true. We can conclude that Q is true, which we should be writing in words. So Q is Mark can buy the video game. Can buy a new video game. This one, our conclusion would be quadrilateral ABCD is a parallelogram. Number 3 says, if you are 18 years old, that'll be P, then you can register to vote. That'll be Q. Olivia is not 18 years old, so we're given not P. Remember, that's not a way to make a valid conclusion with the law of detachment. The two things we're looking for is either P or not Q. Those are the two things that let us make a conclusion. Not P does not let us make any valid conclusion at all in a normal conditional statement like this. This one says if the sum of the measures of two angles is 90 degrees, then they are complementary. This one's interesting, and I'll come back to it, but we have this is P, and this is Q, and it says measure of angle J is 58 degrees, measure of angle K is 32 degrees. That means we can think of this as being P. The sum of measure of angle J and measure of angle K is 90 degrees. So we do know our hypothesis, so we can conclude that angle J and angle K are complementary. So this one is interesting because it says if then, but this is a definition. So this sum is 90 degrees is complementary. So this is what we call a definition. It's the kind of thing we write in our notebook as a definition. Whenever we have a definition, definitions are always biconditionals. So they didn't write it as one here, but we should technically write this not as if. We should say the sum of the measures of two angles is 90 degrees if and only if they are complementary. Meaning our conditional should look like this with the double arrow and be a biconditional. So any definition is always a biconditional, but it's okay. They didn't present it this way, but the reason I wanted to point it out, because if they said measure of angle J and measure of angle K are complementary, your instinct tells you, yes, you could conclude that their sum is 90 degrees. And the reason you feel that way is because this one should be written as a biconditional, not a regular conditional. That allows us to say that not only are the conditional and contrapositive logically equivalent, but also the inverse and converse are true as well. And the last one, if you plan to attend prom, that will be P, then you must purchase a ticket. That's Q. Sarah purchases a prom ticket. That is Q. So we cannot draw any valid conclusion from this pair of statements. Remember that if it said Sarah did not purchase a prom ticket, we could actually conclude that she is not planning to attend prom. So that would be using the contrapositive and using not Q to draw a conclusion about not P. All right, then let's move on to the other one. So law of detachment is the first logical tool we have for deductive reasoning, and the law of syllogism is the other one. So this one is not about a single conditional, it's about two conditionals. So we have if P, then Q, and if Q, then R, we conclude a conditional that basically you can think of it as just chaining them together. So if I write these out, if P then Q, and if Q then R, you can see that these chain together. So it's like saying A is equal to B is equal to C, therefore A is equal to C. It's kind of like replacing, right? It's substituting this Q for R to make it if P then R. So that's the conclusion we draw here, is the law of syllogism lets us chain conditionals together to make a like a conditional that kind of squishes them all into one. And you could chain as many statements together as you wanted. You could have if P then Q, Q then R, R then S, S then T, and squish them all together to say just if P then T. So it's like a chain of reasoning that we condense down based on this idea of like substitution, basically. So the easy thing to get mixed up here is if the order doesn't match. Because if we think about equal signs, if I said if A equals B and C equals B, then I could conclude A equals C. The reason we can do that is because these are basically, equal signs are like a biconditional. There's no direction to them. So it might be better to think about it like an inequality. So if I say A is less than B and B is less than C, I can conclude A is less than C. But I can't do that, so that one is good, I can do that. But I can't do that if I say A is less than B and C is less than B. I cannot conclude that A is less than C. That one is no good. And we could easily pick some numbers to show that, right? I mean, conceptually, you probably understand that, but let's pick some numbers and say A is 1, B is, I don't know, 40, and C is -5, and B is still 40, right? It has to be the same number here. But A, 1, is not less than -5. So this line of reasoning doesn't work because the inequality symbol is directional, just like these arrows are. So basically this thing called a converse error is saying that if we have if P then Q, and if R then Q, we can't chain these together. So this is no valid conclusion because it's like saying P is less than Q and R is less than Q. That does nothing to relate P and R to each other. So hopefully this connection to earlier math with the equals and the inequalities helps you to see how that works. But this right here, I guess I should put it in right. This right here is the most common way that we mess up logic and that we create logical fallacies. So be watchful for it, that we need the conclusion of the first conditional has to be the hypothesis of the second conditional. That's the only way that it works to chain them together. So let's look at some examples and see if we can figure them out. So it says, if it is Saturday, we'll call that P, then Jake has a baseball tournament, Q. Then we have a second conditional. So we know that we're not looking at law of detachment here, we're looking at law of syllogism. If Jake has a baseball tournament, that was Q, so we rename that again as Q because it's the same thing. Then he will need to pack his lunch. That's a new statement, we'll call it R. So the first sentence says, if P, then Q. And the second one says, if Q, then R. Okay? So since we have that, we're allowed to chain it together and basically get rid of the statement about the baseball tournament. We can say, if it is Saturday, then Jake needs to pack his lunch. Jake needs to lunch. I'm just going to shorthand it. So we get rid of that part about the baseball tournament because it doesn't actually matter from the original premise to the final conclusion. It's just kind of drops out. This one we have if a number is divisible by 12. That's our first statement. Then it's divisible by 6. That'll be Q. If a number is divisible by 6, that's Q again. Then it is divisible by 3, and that's R. So again, we have if P then Q, and if Q then R. So we can conclude if divisible by 12, if a number is divisible by 12, then it's divisible by 3. And we can get rid of this idea of divisible by 6 because it's just an intermediate step linking them together. So one thing to watch out for here is when things are written in common language like this, make sure that it's written as if-then. So I think we talked about in conditionals that if it's written in common language and it's not written as if-then, first you want to rewrite it as an if-then so that you're sure what's the hypothesis and what's the conclusion. So just remember to do that. If a quadrilateral is a square, so that'll be P, then it is a rectangle, that'll be Q. If a quadrilateral is a rectangle, that was Q again, then it has 4 right angles, that's R. So this chains together correctly. So if a quadrilateral is a square, then it has 4 right angles. So that is valid. And since those are both true, we can think about that and think, yeah, a square does have 4 right angles. If it is sunny this weekend, we'll call that P, then you will go boating. Now, that sounds like it may or may not be true, but remember, we're not judging the validity or the truth value of this statement. Since it's given, it is true. If it's sunny, we will go boating, whether we want to or not. If it is sunny this weekend, then you will wear shorts. That is the same hypothesis as the first one. So we can't conclude anything using the law of syllogism. So I'm going to put none, but I do want to address the fact that we can make a conclusion. It's just not using the law of syllogism. So we know that if it's sunny, we'll go boating, and if it's sunny, we'll wear shorts. So we can condense this and say, if it's sunny, then both of those are true. The way we would write that using our symbols is if P, then, and we would write Q and R. So that says if P is true, then the conjunction of Q and R is true. That doesn't come from the law of syllogism, so here we're still putting none because that's not how we're coming up with that information. We're just rewriting our logical argument using symbols. This one says if you shop at Target, then you will use your Target red card. Again, may or may not be true, doesn't matter, it's given, if P then Q. If you do not use your Target red card, so that says if not Q, then you will not get 5% off, not R. So this one doesn't directly chain together because this is P to Q and not Q to not R. So the first step we want to do here is fix this second one to get rid of the negations. We do that by writing it as its contrapositive. So instead of not Q, then not R, we write R, then Q. That is the contrapositive of this one. So now we can discard that, and we see that we have P to Q, R to Q, and we know we cannot conclude anything from that because the conclusion is the same for both. Technically, we could conclude if P or R, then Q, but again, I think we can conclude that. I don't know. We're not even looking at that now. We're looking at law of syllogism, so we won't worry about that right now. But yeah, so it says if P then Q, or if R then Q. So we could say if P or R then Q, but that's not using law of syllogism. So again, that's just kind of a side thought. It's not really our topic here. And then we have if it snows, then school will be canceled. So if P, then school will be canceled. If school is canceled, that's Q, then students will need to make up a day of school. Yes, that chains P to Q, Q to R. But this last one highlighted a really important thing of watching out for negations to make sure that we're not comparing Q and not Q. So you could even think about this as being if P, then not Q, because school is canceled. So you could say there's no school, but as long as it's the same thing, right? So this is school is canceled and this is school is canceled. So those match. Neither of them is the negated version. So we can just say if it snows, then we have to make up a day of school. So that's how that one works. Remember that if it doesn't directly chain, like 6, 7, 8, and 11, then we say we can't conclude anything using the law of syllogism. And remember that it's easy to tell this apart from law of detachment because there's two separate conditionals here, whereas in the law of detachment, there's just a conditional and then a single statement rather than two conditionals.